Hi guys, this is the video to show you how to calculate partition coefficients for a substance or for a solute between two immiscible solvent. Now first we talk about the definitions of partition coefficients, right? So it is all about the distributions of a solute between two immiscible solvent. Now what is that immiscible solvent? Immiscible solvent means like water and oil. When you mix them together, they can't mix. Basically, they will give you two layers when you mix them. No matter how hard you shake them, at the end, it will still separate into two layers. So that's what we call immiscible solvent. All right. So it depends on how the solute distribute between these two immiscible solvent. Let's say, for example, since we talk about water and oil, if you put water and oil together and mix them, you will definitely get two layers, right? And which one is on top layer, which one is underneath, that depends on the density. So let's say I have water and oil together in a beaker. All right, basically they can mix. Now I drop in an organic compound. Let's say, for example, I have ethanoic acid. All right, so which one do you think the ethanoic acid will go to? Now, first, ethanoic acid is CH3COOH. So this molecule is actually a polar molecule. So because the presence of the OH, it can form hydrogen bonds with water. So can it dissolve in water? I would say yes. All right. But at the same time, can these ethanoic acid actually dissolve or mix with oil? I would say yes as well, because organic compound, or is an organic compound which is nonpolar, and then this ethanoic acid is also nonpolar. So they are miscible. So these solutes are actually free to move between oil and water. But then we still have to look at the solubility, whether the ethanoic acid is actually more soluble in oil or more soluble in water. All right, so how do we know that? The distributions, whether they are in water more than in oil or the other way around. So we look at the partition coefficients. All right, now partition coefficient, usually we put it as KPC. It's a constant value equals to a solute. Let's say, for example, like what I said just now, I have ethanoic acid, CH3COH. This concentration of these solutes in one of the solvent divided by the concentration of the same solute in another solvent, and these two solvents should be immiscible. They can't mix. All right. Now, how do we put that in? Ethanoic acid is supposed to be more soluble in oil because ethanoic acid is an organic compound. It belongs to the same family, which is non-polar in a way, because you have carbon and hydrogens, right? You only have OH there. So it should be more soluble in oil compared to water. Therefore, we put the more soluble here, oil, and this is water. Okay, this is always the case. So the one with higher solubility, we put it on top, and then the other one should be underneath, and then we divide them. All right, so this is how we put the expression. Now KPC, the bigger the value, it means the more soluble it is, the ethanoic acid in the oil, right? Mathematical way, if the ethanoic acid is less soluble in oil but more soluble in water, then obviously the KPC will be smaller. So this partition coefficient constant will give us an idea on how or what is the solubility of a solute between two solvents. Okay, so this is how we determine that. Now, come back to this question. Now, this is just a basic introduction because you've gone through the content, you should be able to you have learned that, right? So let's erase that. So we're going to start out with these questions. Now, the partition coefficient of substance X, which is unknown, between methylbenzene and water. See that? These two are the solvents. Okay, and they are immiscible. They can't mix. Methylbenzene is organic, water is polar, so they can't mix together, just like oil and water. And the solid here, we look at X, is 8. So KPC equals to 8. This is given. All right, X being more soluble in methylbenzene. So we know that when we write the KPC expressions, it should be concentration of X in methylbenzene divided by concentration of X again. It should be the same solute because we only consider one solute at a time, and this one should be in water. So this is how we write that, n equals to 8. All right, and there's no unit for this KPC because it's concentration divided by concentrations, so it cancels out. Now, next thing is, what mass of X will be extracted from 100 ml of an aqueous solution, means water, containing 6 grams of X, okay, by shaking it with 1 portion of 100 ml methyl benzene. So what does it mean here from the questions? It says that I have 100 ml of water with 6 grams of X in it initially. All right, so this is the separating funnel. Okay, inside I put in first layer. Of course, I close this valve. Here is 100 ml of water, which is aqueous solutions, containing what? 6 grams of X initially. All right, then I put in the new portions. What is that? I put in another layer. This is actually the methyl benzene. Sorry. See that? I put in 100 ml of methyl benzene. All right, so you have 2 layers here. One is the water, all right, and one is the methyl benzene. So what next? According to the steps that you have learned, you should shake them for a few minutes. Why do you shake them? Because you provide kinetic energies to the solute, which is this, the 6 grams of X. Okay, it's a substance X, and you provide kinetic energy for the X to move around between water and methyl benzene, knowing that it is more soluble in methyl benzene. So when we shake them, we expect the X, the 6 gram of X, will start moving from the water to the methyl benzene layer. But would it 100% move to it? We are not sure. Right? This is what we need to calculate, because they're asking what mass of X will be extracted from 100 ml by shaking with 100 ml of methyl benzene. So how many grams of X will move from water to methyl benzene? Given that the partition coefficient is equals to 8. Like I said, this is a constant value unless the temperature change. Otherwise, partition coefficient is always constant for these particular systems, of course. All right, so what we're going to do now is we're going to show you the calculation for part 1. Okay, let's start with the calculations. Question 1. So we know that KPC equals to 8 concentration of X in methyl benzene, all right, over concentration of X in water equals to 8. And how do we put in the concentration of methyl benzene? How do we know that? The only information is 6 grams, guys, and X is unknown. Can we use the 6 gram and convert it into mole by dividing molar mass? Theoretically, yes, but we can't do that. Why? Because X is unknown. We don't have the molar mass, so we can't get the concentration. We can't get mole. All right? But bear in mind, concentration can be in mole per dm cube, or it can be in gram per dm cube. So if it is in gram per dm cube, we don't need the molar mass. We have grams. We can straight away get the concentrations. You got that? So now let's check. All right, the solution is X methyl benzene over X in water equals to 8. And what will be the gram per dm cube of X that moved to the methyl benzene? Unknown, right? So we put Y grams divided by, because it's gram per dm cube, so divided by what? What is the volume of methyl benzene? 100. So 100 over 1000. I change it into dm cube. That is in methyl benzene. All right, so I expect Y grams move to it, unknown, divided by how many grams remain in the water. Initially, I have 6 grams, guys. So 6 minus Y, because Y has been moved to methyl benzene. So 6 minus Y divided by, what is the volume of aqueous solution? Still 100. The same thing, guys. 100 over 1000 equals to 8. You see that? And the volume can be cancelled out. So eventually you get Y grams over Y gram per dm cube over 6 minus Y equals to 8. See that? And then, of course, you just solve it using your mathematical way. So what we're going to do is we just times it. Y equals to 48 minus 8y. All right, so 9y equals to 48. So y equals to 48 divided by 9. You get 5.33 grams. So this is the mass of X that being extracted from aqueous solutions to the 100 ml methylbenzene. So the first one done. Okay, this is the answer for the first questions. Right, let's move on to the second one. Let's erase that. All right, second question, guys. What about two successive portions of 50 ml methylbenzene? Now, what does it mean by two successive portions? Just now, we were using one portions of 100 ml, right? We put it in and we shake them. So we just done it once. But now, instead of using 100 ml to shake once, I split it into two portions, 50 and 50. So I shake with the water twice. First time, I shake it with 50. All right. Once it's done, I remove the water layer. Sorry, I remove the organic layer, the 50 ml, and I mix it with another new fresh portions of methylbenzene and shake again. So which means we try to extract it using 50 ml each, but 2 times. Okay, let's see what's the difference. Now, we still do the calculation as usual. X in methylbenzene over X in water, and it's equals to 8, right? But now I'm using different volume, right? I'm using 50 each successive portions. Let's say this is the first round. So what happened here? I'll do the same thing, guys. Y grams over no longer 100 because I'm using 50. 50 over 1000 divided by 6 minus y, because initially I have 6 gram minus y grams. This is gram. So that's gram over water still maintained as 100. So 100 over 1000. That's how we do it. Equals to 8. See that? So then we solve the mathematical equation, so which is equivalent to, I continue here, y over 0.05 divided by 6 minus y over 0.1 equals to 8. All right, and then we solve the equations. So y over 0.05 equals to 8 multiplied with 6 minus y over 0.1. And then we solve these, we will get the y value here. That's the first portions. Okay, and you do the calculations here. So you will get the first mass. This is the first portions. I'm using 50 ml of methylbenzene, and then I get a mass here, right? This is the first portion, y. Done first portions. Then we discard the 50 ml. Now I add in another 50 ml into the same water solutions, and then we shake again. All right, we shake again. So then, sorry, I have to erase that. Second portions is Z grams, for example, over 50 divided by 1000 or 0.05. All right, divided by, is it still 6 minus Z? No, it's actually using the Y just now. Y, 6 minus Y, the remaining, minus Z grams over 100 divided by 1000 or 0.1. You see that, guys? Do you understand this part? 6 minus Y gram is, Y gram moved to the first portions, right, just now? And then, of course, 6 minus 1, I have the remaining. And that's the remaining I'm reacting with the second portions. So I'm using 6 minus y grams minus another z gram that moved to the new portions. And then you continue this calculation equals to 8. You will get the z grams. Okay, you will get a value here. See that? Now, after you have done these two calculations, you do the same thing here. You add up both. First portion, how many grams moved to the methabenzene? Y grams. Second portion, how many moved to the methabenzene? Z gram. So you add these two up, you get a total mass being extracted. Make sense? Now, one thing I can tell you, the total mass being extracted here will be bigger than if you're using 1 portions of 100 ml. Alright, so remember just now, if I'm using 1 portions of 100 ml, I'm getting 5.33 grams, right? So I can guarantee you, if you do the calculation here, the total mass being extracted by using 2 successive portions, it is definitely higher than 5.33 grams. So what does it mean? It means if you're doing an extractions, the more portion you use, the better the extraction, the better the result. For example, just now it's 100, I reduce it, I split into 50-50, right? What if from 100 ml, I split it into 25, 25, 25, 25? So I need to extract 4 times, each 25 ml. Now, at the end, I'm using the same total methabenzene, which is 100 ml, but just that I split it into 4 portions, 4 successive portions, and then at the end, I expect the total mass being extracted is much higher than this and this. So the smaller the portions, the more extraction you did, the more mass being extracted. All right, you can even actually reduce it, like 100 ml in total, I can break it down into 10 rounds, 10 portions, 10 ml each. So I can carry out the extraction 10 times, and then I expect the total mass extracted into the methabenzene will be higher at the end. Okay, now it is difficult to get a partition coefficient that is perfect, which means it is difficult to get 100% extractions. Like I have 6 grams just now. Is it possible for all 6 grams move to the methabenzene, 100% conversion, 100% extraction? No. You may get 5.9, 5.89, but 5.99, you can't get 100% because the partition coefficient is given as 8. So no matter how you calculate or how many times you've done it, you still can't get, you can get a close value to 6, but you still have some remaining, even 0.0001 grams that remain in the aqueous solution, that still consider certain percentage, so still not 100%, right? So always remember, partition coefficient is constant unless the temperature change. All right, so I leave it to you for this calculation, the simple calculations, and then you tell me whether, yes, do you get a mass which is actually higher if you're using 2 successive portions, or no, 1 portion is actually better than 2 successive portions. Post your answer in OL, the space provided, after you watch this video, and then I want to see your calculations. All right, okay, thank you. Just a short video.